Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. This is lesson 1 from module 3, integer sequences. Should you believe in patterns? Classwork opening exercise says Mrs. Rosenblatt gave her students what she thought was a very simple task. What is the next number in the sequence? Okay, let's just stop right there. Okay, so I decided to go back and talk about what a sequence is before we begin. A sequence can be thought of as an ordered list of elements. So they're in order and they're a list of elements. The elements of the list are called terms of the sequence. So this is a sequence. It's an ordered list of elements, and this is the first term, second term, third term, fourth term in an ordered list. That is called a sequence. Okay, so after going over that, let's move on. So she asked the class, what is the next number in this sequence? In other words, what's the fifth element in the sequence? We have 2, 4, 6, 8. What do you think is the next term? Cody said, I'm thinking of a +2 pattern, so it continues 10, 12, 14, 16. Allie says, I'm thinking of a repeating pattern, so it continues 2, 4, 6, 8, 2, 4, 6, 8. Suri says, I'm thinking of the units digits in the multiples of 2, so it continues 2, 4, 6, 8, 0, 2, 4, 6, 8. Are each of these valid responses? Okay. Well, is there a pattern here? 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 0, 2, 4, 6, 8, 0. Since it is a pattern, then they are valid. So the answer is yes, because they are patterns. B says, what is the 100th number in the sequence in Cody's scenario? So in this one, we have the first, second, third, fourth. What would be the 100th? And then what is the 100th in Allie's, and what is the 100th in Suri's? Okay, so Cody, the 100th would be, well, 10, 12, 14, 16. That's 1, 2, 3, 4. How high would those go, counting in twos? What would be the 100th number? Okay, so as sequences, we want to think about patterns here. So if we're talking about Cody, he started with 2. There's my first term was 2. My second term was 4. My third term was 6. My fourth term was 8. So all you have to do is multiply your term by 2, and that's the number you're going to be at. So if it says what is the 100th number in the sequence of Cody's scenario, then I would just take 100 times 2, and that should be 200. Okay, Allie says hers is 2, 4, 6, 8, and it repeats. Well, this is 4. This is a sequence that has repetition after 4 terms. 4 terms, repeat 4 terms, repeat 4 terms. Well, 100 divided by 4 is 25 with no remainder. So there's going to be 25 groups of 4 ending on the 8. So Allie's 100th term will be 8. Okay, this is a list of, or a sequence with 5 terms that repeat over and over. Okay, so if I took 5 and took 100 and divided it by 5, I get 20 with no remainder. So that means it's going to repeat 20 times entirely without any leftovers. So the last term is going to be the last term of the repetition. So therefore, Suri is going to be 0. Okay. All right. C says, what is an expression in terms of n for the nth number in the sequence in Cody's scenario? Okay, so one example is, well, we know that the terms multiplied by 2, so we could say 2n. So the 10th term would be 2 times 10 or 20. Another response might be multiplying 2 times, now we're leading up to something here, and if the first term is 2, what did we do to 2 to get 2? What did we do to that to get 2? Okay, term number 1 plus 1 equals 2. So the first term, or the 0, n equals 0, we'd have to start at n equals 0 for this one. So 0 plus 1 is 1, 2 times 1 is 1. N times, so the second term would be 1. 1 plus 1 is 2, 2 times 2 is 4. So in this case, we'd have to start at if n equaled 0, or if we started with 0. So I should say if starting at n equals 0. Example 1. Jerry has thought of a pattern that shows powers of 2. Here are the first 6 numbers of Jerry's sequence. 1, 2, 4, 8, 16, 32. Write an expression for the nth number of Jerry's sequence. Okay, in order to explain this, I decided to create tables here. So Jerry has thought of a pattern that shows the powers of 2. Here are the first 6 numbers. So we have 6 terms. 1, 2, 3, 4. Let's see. There we go. 1, 2, 3, 4, 5, and 6 term numbers. So the first term was 1. The second term was 2. The third term was 4. And then we went to 8. And then we went to 16. And then we went to 32. So the first term's 1. How did we get that? Well, 1 plus 0, we could add 0. 2 plus 0 is 2. 3 plus 0, then it fails. 3 plus 0 is not 3. So it's not just adding 0. We could say times 1. 1 times 1 is 1. 2 times 1 is 2. 3 times 1 is not 4, so it's not times 1. So we're trying to figure out a rule that will make this true. But there's a key term here. And it is powers. Okay, so Jerry has thought of a pattern that shows powers of 2. So 1 squared is 1, 1 times 1, but 2 squared is 4, 3 squared is 9, so it's not just simply squared. So we have to think about this for a bit and try to figure out what is going on here. Okay, so we are told that the base is 2. Powers of 2. That means it's 2 to the power of something. Okay, so 2 to the power of what would give us 1? 2 to the power of what will give us 2? Well, that's 2 to the first power. We know that. 2 to the power of what will give us 4? Well, that's 2 squared. 2 to the power of what will give us 8? That's 2 to the third. 2 times 2 is 4 times 2 is 8. And then 2 to the fourth would be 2 times 2 is 4 times 2 is 8 times 2 is 16. So this seems to be what's the rule. So 2 to the fifth is 2 times 2 is 4, which is 2 times 2 times 2 times 2 times 2. 2 to the fifth means 2 multiplied by itself 5 times. 2 times 2 is 4 times 2 is 8 times 2 is 16 times 2 is definitely 32. So what would it be for up here? 2 to the 0. Anything to the 0 power is 1. Okay, so now it says sequence terms. Okay, we're going to use subscripts here. So if I write the letter A with a little 1 down below, that just means A sub 1. We say A sub 1 and it means the first term in the sequence. And so the little subscript number tells us the number of the term. So this just gets us familiar with this type of this way of writing. So A sub 1, A sub 2, 3, 4, 5, and 6. Instead of just numbering them 1 through 6, we call that A sub 1 is the first term, A sub 2 is the second term, and then A sub n is what we would lead up to. A sub n is the last term. So the new notation that we're familiar with is function notation. F of 1, F of 2, F of 3. Struggling here. Write the same thing twice. F of 4. F of 5. And F of 6. That would always lead up to our last term that we're going to call F of n. And that's just basic function notation. So in this case, these terms would repeat as well. 1, 2, 4, 8, 16, 32. So now that we've come up with this notation and we're saying it's 2 to a value, well, if our first term is 2 to the 0, then we want that to be what? We want to say that this is, what's our rule for this function? We want to say 2 to the what? What power in terms of n? It can't just be 2 to the n because the first term would be 2 to the 1, which is 2, and that's the second term. So what do we have to do if n is 1? That was weird. If n is 1, what do we have to do to get 0? Well, we have to subtract 1 from it. If I said 2 to the n minus 1 and I substitute in this 6, 2 to the 6 minus 1 is 2 to the 5th power. So our sixth term is 2 to the 5, 2 to the 6 minus 1. So 2 to the 5th is 32. So this would be our rule. 2 to the n minus 1. And that starts with n equal to 1. 1 minus 1 is 0. 2 to the 0 is 1. Consider the sequence that follows a +3 pattern. 4, 7, 10, 13, 16. Write a formula for the sequence using both a sub n notation and the f of n notation. So I'd write a sub n equals, and our first term is, what do we have to do to 1? So this is our first term. That's a sub 1. If a sub 1 equals 4, how do I come up with a sub n? I have a sub 2 equal to 7. Or another way I could say that is f of 1 and f of 2 are 4 and 7 respectively. What is the rule to get this 4? How do I get this 4? How do I get this 7? How do I get this 10? So I just start to think about this, and I'm like, well, if I say a sub n equals 4n, and my first term, a sub 1, is 4, so 4 times 1 is 4, that works. But then when I go to the second term, 4 times 2, second term, 4 times 2 is not 7, it's 8. So that does not work. So what do we have to do to make this work so it's not 4n? So we just try to play around with this. There is a way to do this. Eventually we'll lead up to it. But in this case, if we multiply by, so we're doing something to 1 to get 4. We're doing something to 2 to get 10. So with n in mind as well, it's not n times 1, it's not 4 times n, it's not 3 times n. 3 times n would be 3. 3 times 1 is 3. So we're trying to figure out how to get n over here to a mathematical expression that will equal 4. So if n is 1, what do I do to 1 to get 4? Well, I can add 3, so I could try that. So I could say plus 3. But then when I get to my second term, and I add 3 to it, I don't get 10. So just adding 3 doesn't work. So if I multiply it by 2, so I just play around with this until we figure out a rule for this. If I tried a 2, so if I said 2, and I need it to equal 4, by the way, the first term, 2 times 1 does not equal 4. But if I added 2 to that, then that does equal 4. So there's my first term. So then if I take my second term and use the same rule, my second term, and add 2, do I get 10? Well, that's 4 plus 2, and that definitely does not equal 10. So 2 times n plus 2 didn't work. So then I'm going to just try changing my coefficient here and seeing what will work. So then if I just change this to a 3, let's just erase all this. So now I'm going to have 3n and 3n. Well, 3 times 1 does not equal 4. Actually, I don't want to put an n in there. I want to put a parentheses 1. And 3 times 1 does not equal 10. But if I take 3 times 1, that's 3, and I add 1 to it, then that's 4. And this is my second term. Well, 3 times 2 is 6. 6 plus 1 is 7. And, okay, I wrote 10 down here by mistake. That's my third term because I just noticed something here. That is my second term, 7. 3 times 2 plus 1 is 7. 3 times 2 is 6 plus 1 is 7. So once we start figuring out that this might work, we continue and check the next one. So my third term would be 3 times 3 plus 1. Well, 3 times 3 is 9 plus 1 is 10. My fourth term would be 3 times 4 plus 1. And 4 times 3 is 12 plus 1 is 13. And sure enough, it's 13. So it looks like we found a pattern where our term number is my n. So I would say a sub n equals 3 times the number term plus 1. Or I could call it f of n equals 3n plus 1. Part B says, does the formula f of n equals 3 times n minus 1 plus 4 generate the same sequence? So let me just erase this. So we want to try, the first term would be 1 minus 1, which is 0. 3 times 0 is 0. 0 plus 4 is 4. My first term is 4. That worked. Okay, first term does work. Then I can't just try 1 and say, yes, it works. I want to keep trying. So the next term would be the second term. So 3 times 2 minus 1, which would be 3 times 1 plus 1, which would be 3 plus 1 equals 4. And that is not my second term. Oh, it's not plus 1, it's plus 4. Plus 4, plus 4. 3 plus 4 does equal 7. So that checked. So I'm not going to be satisfied with just 2, so I'm going to try another one. So I'm going to take 3, third term minus 1 plus 4, 3 times 2 plus 4, 3 times 2 is 6 plus 4 is 10. So that checks as well. Try the next one. Fourth term, 3 times 4 minus 1 plus 4. Well, this is 3 times 3 plus 4, which is 9 plus 4, which is 13. And then 3 times the fifth term minus 1 plus 4 is 3 times 4 plus 4, which is 12 plus 4, which is 16. And all of these worked. So does this formula generate the same sequence? And the answer is yes. Why might some people prefer this formula over the previous one? Okay, before I answer this question, I want to show you a quicker way of seeing if this is equivalent to this. Okay, so if I take, I'm going to do it right here. If I take 3 to the n plus minus 1 plus 4, and I distribute, I get 3n, and I distribute, and I get minus 3, and then I have the plus 4 following, then I take, the 3n stays 3n, and minus 3 plus 4 is plus 1. And that's what we had right here. And the reason some people might prefer this formula would be because the first term in the sequence is a term in the formula. So this plus 4 is your first term instead of plus 1. Since there is the 3 plus pattern, okay, we're adding 3 every time. Since there's an adding 3 every time, the nth term is just the first term plus that many more 3's. So the first term plus that many more 3's. Okay. Part C. Graph the terms of the sequence as ordered pairs n, f of n on the coordinate plane, and what do you notice about the graph? So I need a table. So my n is my independent variable, and my f of n is my dependent variable. And if I start with the term numbers 1, 2, 3, 4, 5, then I get 4, 7, 10, 13, 16. So the point 1 comma 4 is over 1 up 4, which is here. And then 2, 7 is here. And then 3, 10 is here. And then 4, 13 is here. And then 5, 16 is here. If I get my ruler out and connect those dots, then we see that it is a linear pattern. And the y-intercept is 3. The rate of change is 3. That is our slope, if you will. Rate of change of 3. So it's a linear equation with a slope of 3 and a y-intercept of 1. Okay, I've got my dot in the wrong place. My line is off just a little bit, so that would continue down and it'd go through 1. Okay. Exercise 1. Refer back to the sequence from the opening exercise when Mrs. Rosenblatt was asked for the next number in the sequence 2, 4, 6, 8. She said 17. The class responded, 17? Yes, using the formula f of n equals 7 over 24 times n minus 1 to the 4th power minus 7 over 4 times n minus 1 cubed plus 77 over 24 times n minus 1 squared plus 1/4 times n minus 1 plus 2. Does her formula actually produce the numbers 2, 4, 6, and 8? Okay, so I decided to graph this using Algebra website, and because it'd be to plug in a 2 here, you get 2 minus 1 is 1, 1 to the 4th power is 1, so you get 7 over 24 minus 7/4 plus, you're getting 1 every time inside here, so it's just this plus that, or this minus this plus this, and it's a lot of math, so I decided to plug it into GeoGebra, and there's the formula here. It doesn't show the whole thing, but it's all there. Actually, I can show the whole thing. So just to show you that it does match, here is her formula. It's copied in here, and then I plugged in the points 1, 2, 2, 4, 3, 6, 4, 8, and 5, 17. And looking at the graph, sure enough, those points are all on that graph. So yes, this formula does work as long as the next term is 17. Then it says, what is the 100th term in Mrs. Rosenblatt's sequence? So I'm just going to do it here, the 100th term. So I would have to go all the way out to 100, which is right here. So I'm going to draw a vertical line at 100. Okay, so I'm going to try this using the graph. So I drew a vertical line at 100, and I want to know when her 100th term, what the value is on the function. So I'm just going to scroll up here, and as you can see, that blue line is moving to the right pretty slowly, but it's moving. Okay, I don't know how far I have to go. I'm going to pause this video so I can get there. Okay, so I got all the way up to 18,000, 19,000, 20,000, and I'm nowhere near. So let's do this algebraically. Okay, so this took a really long time, so I just did it behind the scenes. F of 100 would be 7 over 24 times 99, because 100 minus 1 is 99, to the 4th, minus 7 over 4 times 99 cubed, plus 77 over 24 times 99 squared, plus 1/4 times 99 plus 22, and it comes out to be 26,350,832. Okay, so just for kicks, I scrolled up to our answer on the graph, and they did put a dot where this does intersect. A little more than 26,350,000. So it should be 832. So I'm going to scroll in. Come on, computer's struggling with it. 26,350. Okay. Anyhow, it's 26,350,000, 500, 600, 700, 800, and then 32 would just be a little bit above that. So it does actually cross right there. Okay. Number 2 says, consider a sequence that follows a -5 pattern. It decreases 30 to 25 to 20 to 15 and continues. Write a formula For the nth term of the sequence, be sure to specify what value n your formula starts with. Okay, so I know this is in multiples of 5. We're subtracting 5 each time. So I know that there's a factor of 5 in there. 5 times a number. So 6 times 5 is 30, but 5 times 5 is 25. So we're decreasing as we go to the right. 5 times 4 is 20. 5 times 3 is 15. So if we're multiplying by 5, we have to subtract that product from something. So with n equals 1, 5 times 1 is 5. What do I subtract 5 from to get 30? And the answer is 35. So 35 minus 5n, 35 minus 5 times 1 is 30. 35 minus 5 times 2, 5 times 2 is 10. 35 minus 10 is 25. Make our third term n3. 5 times 3 is 15. 35 minus 15 is 20. And n is 4. Fourth term, 5 times 4 is 20. 35 minus 20 is 15. So I would say f of n, or a sub n, equals 35 minus 5n. Start with, be sure to specify what value n your formula starts with. Starting with our first term, so that we're going to call it n equals 1. Okay, finding the formula is the trickiest part, but now it says to find the 20th term. So that'd be f of 20 equals 35 minus 5 times 20, which is 35 minus 100, which is negative 65. Okay, now it says to graph the terms of the sequence as ordered pairs n comma f of n. So we have n, f of n, and we're starting with 1. So 1, 2, 3, 4. And what values did they give us? First term was 30, 25, 20, and 15. So 1 comma 30 is right here. 2 comma 25 is here. 3 comma 20, 4 comma 15, and so on and so on. So there it is, graphing the terms of the sequence as ordered pairs on the coordinate plane. So it's linear with a slope or a rate of change of negative 5 and a y-intercept of 35. Consider the sequence that follows a time pattern 5, 1, 5, 25, 1, 25. Write a formula for the nth term of the sequence. Be sure to specify what value of n you start with. Okay, so it's going to be f of n equals, I know this is exponential, and 5, it's got a pattern that changes in 5, so there's going to be a 5 involved. And I know this is exponential because 5 to the first power is 5, 5 squared is 25, 5 cubed is 125, and 5 to the 0 is 1. So I'm going to call this 5n to the n minus 1. So our first term, where we start with n equals 1. So if I put a 1 in there, 1 minus 1 is 0, 5 to the 0 is 1. Put a 2 here, 2 minus 1 is 1, 5 to the 1 is 5, and so on. B says, using the formula, find the 10th term. So that'd be f of 10. F of 10 equals 5 to the 10 minus 1, which equals 5 to the 9th power. Hey Siri, what's 5 to the power of 9?
5 raised to the 9th power is 1,953,125.
Okay, so there you go. Part C says graph the terms of the sequence as ordered pairs. N, f of n. Well, our first term was 1. So the point 1, 1. So that would be like practically on the line down here, because that's 100. So 1 would be way down here. And then 2, second term is 5. Still not up very far, maybe there. And then 3 is 25. That's a quarter of the way up, like that. And then 4 was 125. So 4 is here, 100 and a quarter of the way up would be here. And then 5 would be 5 to the 4th, which is 625. So then 5 would be 6 and a quarter, which is right about here. And then it just starts growing really fast. As you can see, the 9th power is 1,900,000, and this only goes up to 1,000. So that's where I'm going to stop graphing right there, because I'm going to be off the grid with the next one, which is 5 to the 5th. Okay, number 4. Consider the sequence formed by the square numbers. 1 squared is 1. 2 by 2 or 4, 3 by 3 or 9, 4 by 4 or 16. Write a formula for the nth. Okay, these are simply perfect squares, so I would say f of n equals n squared, starting with n equals 1. So 1 squared, 2 squared, 3 squared, 4 squared. Using the formula, find the 50th term of the sequence. That would be f of 50 equals 50 squared, which equals 50 times 50, which is 2 5 and 2 zeros, 2,500. C says to graph the terms of the sequence as ordered pairs. So we're at 1, 1, 2, 2, 3, 9, 4, 16, 5, 25, 6, 36, 7, 49, 8, 64, 9, 81, and 10, 100. And there's our graph. So that looks like a parabola, since it's an x squared quadratic or a degree 2 polynomial. Then it looks like a parabola on the right side. 5 says a standard letter size piece of paper has a length and width of 8.5 inches by 11. Find the area of one piece of paper. So I always tell my students, write a formula, substitute the givens. I'll use parentheses because there's that decimal, and then simplify and solve. So 8.5 times 10 is 85, plus another 1 is 8.5. So 85 plus 8.5 is 93.5 inches squared. If the paper were folded completely in half, what would be the area of the resulting rectangle? Well, we'd be cutting one of these in half, so that would be half of our area. So the area would equal length times width again, where I could cut either one in half. I'll leave the 8.5, but I'll multiply it by half of 11, which is 5.5. And say, hey Siri, what's 8.5 times 5.5?
8.5 times 5.5 is 46.75
inches squared. So 46.75 is half of 93.5. C says to write a formula for a sequence to determine the area of the paper after n folds. So we're going to write f of n equals, and our area of the whole piece of paper, 93.5. And what are we dividing by? Well, we divided it by 2 to get this piece, but if we divide it by 2 again, that's dividing by 2 divided by 2, or divided by 2 squared. So what we're really doing is dividing by multiples of 2. So I'm going to say 2 to the n. So my first term is 93.5 divided by 2. If I fold it a second time, it would be 93.5 divided by 4, because that's a quarter of the paper. You get the idea? And then fold it 3 times, and that's an eighth of the paper. Okay, fold it in half. Half of a half is a quarter, and half of a quarter is an eighth, and so on and so on. Okay, so we're going to start with n equals 1. Okay, we could also have said, now let's just leave it at that. Okay, what would the area be after 7 folds? Okay, so we have f of 7 would equal 93.5 divided by 2 to the 7th, which equals 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, times 2 is 128. So it'd be 93.5 divided by 128. Hey Siri, what's 93.5 divided by 128?
93.5 divided by 128 is about 0.7304.
Okay, and she did say about. It's an approximation. So the area would be about 3/4 of an inch, not quite. Okay, that is the end of lesson 1 from module 3. Review the lesson summary and go do your problem set.